Okay, before we begin, it's important for us to review a couple of things about ions in general before we talk about naming ionic compounds. The first thing that we should talk about is how to figure out the charge of these ions, and we talked about this previously in class, but let's quickly review. First of all, anybody who falls underneath that blue square right there is one that you're going to need to use your deluxe periodic table to figure out the charge of. But all the rest of these guys have got one charge that they always do. This first row, the alkali metals, have got one valence electron, which they will always lose and form a +1 charged ion. The alkaline earth metals form +2 charged ions. Boron and aluminum form +3 charged ions by losing all three of their valence electrons. Carbon and silicon could either gain 4 or lose 4. It's difficult to say. They don't usually form ions at all. Sometimes they do. We'll deal with them a little bit. Nitrogen and phosphorus forms -3 charged ions. Oxygen and sulfur are always -2. The halogen family have got 7 valence electrons. They will rob an electron from anybody to pick up an 8th valence electron. That makes them -1 charged ions. And the noble gases, since they've already got 8 valence electrons, do not form ions under normal circumstances. So that's that. Now what about these guys underneath that blue box there? They're mostly transition metals. And for these transition metals, if you look closely at your periodic table, let's take a look at cobalt here, for example. For cobalt, right above the element symbol is that letter 2, or number 2 and 3. That means that cobalt forms actually 2 different kinds of ions. It forms cobalt with a +2 charge and cobalt with a +3 charge, and either one of them could be present. So as you look at some of these, look at manganese, for example. There's like 5 different kinds of charges on manganese ions, and so that is an important thing that we need to worry about here in just a minute. We'll have to come back to this periodic table in order to find charges of these transition metals. The other thing we should worry about quick is that I passed out a green sheet in class, and on that green sheet are the common polyatomic ions. All of these ions, many of them have names that you might know from your regular ordinary life, like phosphate and nitrate, cyanide, those sorts of things. All these ions are ions that are formed kind of like a compound. There's more than one atom in these ions, and all together they've got either extra electrons or in a couple of cases too few electrons, and so they've got a charge. And so we treat these things like a chunk. That's the biggest thing to worry about here, is that at least for the time being, we're not going to break these guys up into the parts. They're always going to stay together as a chunk. And so when we name these things, we need to be on the lookout for these guys as well. So let's do a couple of examples here. We're going to start off simple. We'll do this in part 1, and then we'll go on and do a second part of this in part 2. And so let's begin at the beginning here. Take a minute, pause the video, and we have the formulas and names here. I want you to produce names for these first 2 formulas and formulas for these first 2 names. Go ahead and hit pause, and then when you come back, we'll go over them together. Okay, so we start off with this first one with the very first thing that we need to do is name what the cation is, the positively charged ion. It's always written first in a chemical formula, and Ca is calcium. After we name the positive ion, we have to ask ourselves this question. Does calcium form more than one kind of ion? Does it form ions with a couple of different charges? Are there more than one possibility for this ion? And calcium is an alkaline earth metal. It always forms charges with a always forms ions with a +2 charge. So we know that we don't need to use a Roman numeral in this case. So then we simply go on and name the anion, the second half here, which is chlorine, but since it's been changed to negative and it's an ion, we change the ending to chloride. So this first one is calcium chloride. For the second one, again, we start off by naming what this first ion is. Au is gold. Then we ask ourselves that important question, does gold have more than one kind of ion that it forms? And I'm going to click back here to that periodic table that we looked at, and we can see gold right down here. Gold does have more than one kind of charge. It's got a gold with a +3 charge and a gold with a +1 charge. So when we go back to what we were working on here, gold is going to need a Roman numeral, but let's worry about that later. We'll put the parentheses in now. Let's decide what the charge is of gold in just a minute. Then let's go back and name the anion. We have sulfur. Sulfur, when it changes to an ion, is called sulfide. It's a -2 charged ion. So what is going to be the charge on the gold ion? We need to kind of work backwards here to look at this one and figure out what Roman numeral we need to use. Let's think about this. There are 3 sulfurs. 1, 2, 3. And they're not sulfurs actually, they're sulfide ions. Each one has got a -2 charge. Altogether that means that they are -6 in charge. There are 2 gold atoms. Together these gold atoms have to balance out the charge, because you'll notice that there's no charge on this compound, and that's the idea with most ionic compounds, is we don't want to have any charge left when we get the compound together. And so these 2 gold ions have to balance out the -6 charge of those 3 sulfide ions. So together they have to be +6. That means that each of them must be the +3 variety of gold. So those gold ions are the +3 gold ions, and we say that, hey, that's gold with a +3 charge by using a Roman numeral. The name of that compound is gold 3 sulfide. Alright, let's move down to the names here. We've got an aluminum iodide. Let's do some work here to figure this out. Aluminum is an ion that we always know. If you look in your periodic table, it is going to be in the +3 family there. It forms +3 ions. Iodide is a -1 ion. It's a halogen. They're always -1. So if aluminum is +3, let's take 3 iodides together to make a -3 and put them together. Aluminum iodide would be 1 aluminum and 3 iodides. Now you notice I'm not writing the charges in here, because when we get them together like this, there is no charge. The +3 of the aluminum and the 3 negatives of the iodides come together, and now there's no charge, so I don't write anything in that charge place where that exponent kind of looking thing is. There's nothing there because there's no charge when they're together. And finally, the last one in this set is the titanium 4 oxide. So titanium, we ask ourselves, what's the charge on titanium? And it could be a couple of different things, but that is what the Roman numeral is all about. There's no one set charge for titanium, so we need to have a Roman numeral to tell us what that charge is. This is titanium 4. That's the Roman numeral 4, so we know that it is a +4 charged ion. And so what we are going to have to do here is figure out how to balance out that +4 with oxides. Oxides come from the group that is -2 charged. All oxygens have a -2 charge, and so if we take 2 of them together, we get a combined charge of -4 to go with our titanium. So we write our formula. We want 1 titanium and 2 oxides to make titanium 4 oxide. And that's a great example of how that Roman numeral does not mean anything about the numbers in the formula. The Roman numeral tells us the charge on the metal. It tells us this, that the titanium is +4. It does not tell us that we need a 4 anywhere in the formula.